Hello, thanks for clicking. Welcome to another Realist 2 production. Today is our last in our Taylor polynomial approximation series. Today we're actually going to use the equations and apply them to scenarios where we're going to build Taylor polynomials of certain degrees for given functions or given information that's being provided. Okay, so let's actually go ahead and apply this. All right, so let's get started. All right, so the first thing we want to do is I want to write the fourth degree Taylor polynomial for f of x equals sine x at x equals pi over 2. So this represents the center. So the center is pi over 2. That's what I mean by at x equals pi over 2. All right, so now first thing I'm going to do, and I'm going to suggest you do it every time, is the fourth degree Taylor polynomial. We're going to write that formula out so that we can literally just take values, figure them out, and plug them into the formula, and we'll have our answer. We'll see everything we need to be able to get the answer. So t sub 4 is going to be equal to, the center is pi over 2. So it's going to be equal to f of pi over 2 plus f prime of pi over 2, x minus pi over 2, plus f double prime of pi over 2 over 2 factorial, x minus pi over 2 squared, plus f triple prime of pi over 2 over 3 factorial, x minus pi over 2 cubed, plus the fourth derivative at pi over 2 over 4 factorial, x minus pi over 2 to the fourth. Okay? So this is the formula that we got in the last video. All right? We can do it for any degree. In this case, it was degree 4. All right, so now we wrote out the Taylor polynomial. Okay, so now to do this problem, really all you have to do is find f of pi over 2, f prime of pi over 2, f double prime of pi over 2, f triple prime of pi over 2, and the fourth derivative of f at pi over 2, and substitute them all in, and that will give you the final answer. All right, so let's start with f of pi over 2. F of pi over 2 is sine pi over 2. So that's 1. All right. So let's find f prime of x. The derivative of sine is cosine. So f prime of pi over 2 is cosine pi over 2. That's 0. All right. So this term's not even going to be there. All right, we'll write it all out at the end. Let's go to f double prime of x. F double prime of x is negative sine x. F double prime of pi over 2 is negative sine pi over 2, negative 1. F triple prime of x is negative cosine x. F triple prime of pi over 2 is negative cosine pi over 2, 0. And then the fourth derivative of x is, we're at negative cosine, so we'll be back to sine, right, for the derivative. And the fourth derivative evaluated at pi over 2 is sine pi over 2. That's 1. Okay. All right, so now we're going to substitute all of our values in, and that will give us the Taylor polynomial. So I'm going to do it in a different color here. I'm going to do it up here with the one that we just worked with. So f of pi over 2, that's 1. F prime of pi over 2, that's 0. F double prime of pi over 2, that's negative 1. F triple prime of pi over 2, that's 0. And then the fourth derivative at pi over 2 is 1. Okay, so all the 0 terms are going to drop out. This term's going to drop out totally. This term's going to drop out totally. And we're going to write down our fourth degree Taylor polynomial. So our fourth degree Taylor polynomial final is 1 minus 1 over 2 factorial x minus pi over 2 squared plus 1 over 4 factorial x minus pi over 2 to the fourth. And that's the answer. All right, so actually, after all those derivations, the derivation of it is really the tough part. Applying it is actually, for the most part, usually the easiest thing. Like I said, my suggestion is you always write it out first, whatever it is you have to find, write out that polynomial, and then just go find whatever it is they want you to get. All right, let's do the same thing here. So I have a function f of x, has derivatives for all orders x, and I want you to write the third degree Taylor polynomial for f about x equals 5. Okay, so that means the center's at 5. All right, so let's write down our third degree Taylor polynomial. So t sub 3 of x would be f of 5 plus f prime of 5, x minus 5, plus f double prime of 5 over 2 factorial, x minus 5 squared, plus f triple prime of 5 over 3 factorial, x minus 5 cubed. That's my third degree. You don't want to go above that. All right. So now I'm just going to take these values from the table and literally substitute them in. F of 5, that's 3. F prime of 5 is negative 2, x minus 5. F double prime of 5 is 7 over 2 factorial, x minus 5 squared. F triple prime of 5 is 3 over 3 factorial, x minus 5 cubed. And again, you can clean this up a little bit. 3 over 3 factorial would be 2, right? Or 2 factorial again, okay? But that is my third degree Taylor polynomial for this scenario, all right? And again, what can I do with it? It can approximate values near 5, right? Okay, approximate values for this function f of x, all right, using 5 as its. Okay, so let's take a look at our last example here. So suppose that g of x is equal to the integral from 6 to x of f of t dt. I want you to write for me the second degree Maclaurin polynomial to g. All right, so second degree and Maclaurin polynomial. So that means c will be 0. So let's write out our equation over here. So we'll write m sub 2 for Maclaurin, the second degree Maclaurin polynomial. We're writing it to g. So that's going to be g of 0 plus g prime of 0, x. We'll say x minus 0 here for a minute. And then g double prime of 0 over 2 factorial, x minus 0 squared. All right, so let's go clean this up here. So we have g of 0 plus g prime of 0, x, plus g double prime of 0 over 2 factorial, x squared. Okay, so now to be able to do this, I need to calculate g of 0, g prime of 0, and g double prime of 0. Well, let's start with g of 0. So g of 0 is the integral from 6 to 0 of f of t dt. Well, how am I going to calculate that? This is the graph of f. How do I calculate the integral from 6 to 0 of f of t? Well, this means find the area. Integral means find the area under the curve of f from 6 to 0. But the bounds are backwards, so I have to negate this thing to reverse the bounds. So what do I want to do? I want to find the integral from 0 to 6 of f of t dt. I want to find the area underneath the curve of f. So let's go find the area of this thing. All right, so I'm going to cut this into a trapezoid, I think, and a triangle. So that's going to be, the trapezoid is 1/2. The height is 1, 2, 3 units. The first base is 3 plus 6, I guess, plus 1/2 of 3 by 6. So that's negative. 9 times 3 is 27. 27 over 2. 18. Half of 18 is 9. So that's 18 over 2. So that's 45 over 2. So g of 0 is negative 45 over 2 after I find the area under the curve. All right, so that's going to go in there. Now I got to find g prime of 0. So I need to find g prime of x. Well, g of x is equal to the integral from 6 to x of f of t dt. So g prime of x would be the derivative of the integral from 6 to x of f of t dt. Now, the derivative and the integral knock each other out. The numeric bound gets ignored. The variable bound gets substituted in, and I derive the bound. So this is going to be f of x. So g prime of 0 is f of 0. Well, what's f of 0? Well, f of 0 is 3. It's on the graph. So that's 3. G double prime of 0 I got to find. So G double prime of x will be f prime of x. So G double prime of 0 is f prime of 0. Well, f prime of 0 is the slope at 0. Well, that's the slope of the line. So up one, right one. So that's 1. So then that's everything I need. My Maclaurin polynomial is negative 45 over 2 plus 3x, g prime of 0, plus 1 over 2 factorial x squared. And that's the correct answer. Okay? And that's it. That's how we find a Maclaurin or a Taylor polynomial and use the formula in a given scenario to write the equation. All right? As always, thanks for clicking.